Hello, this is my new video. It's about operational amplifier explanation. And so here we see operational amplifier. So what is it? The symbol is a triangle and it has on the left side two inputs which are called in minus and in plus. In plus is often called the non-inverting input and in minus is called the inverting input. And out is the output. So there are two signals coming in, or two voltages coming in, and one voltage going out. It's really about voltage. And the operational amplifier, the op-amp, is not a pure passive component. It has to have a power supply. So as an example, I have drawn here a battery plus and a battery minus, but the voltage, the power supply doesn't have to come from a battery. It can come from any source, like also AC to DC wall plug, or anything really. And as you see here, I will use plus 9 volt and minus 9 volt for these voltages. There are op-amps that can have non-symmetrical input. This means that here at the bottom you would have just ground, and then above you would have like 5 volts. But for the easy of explanation, we'll go with plus 9 volt and minus 9 volt, and you can then transfer that to all other types of supply voltage. So let's start. We have our operational amplifier on the supply with a plus 9 volt, minus 9 volt, and now we can choose whatever we want as an input for the in plus input. I call it in plus. You can say non-inverting input to it, and you can say for the in minus inverting input, but I'll stick for easiness of transfer and referral to this picture. I'll always say for in this video in plus and in minus and out. So to in plus we connect 0 volt, and that is our ground reference, and we draw it as this symbol. So 0 volt at in plus. And again, what's written in green here, it means this is our choice. We could choose anything what we want, but we want 0 volt here right now as an example. You don't have to ground the in plus every time, but now we choose 0 volt. And then for the in minus input, we choose plus 1.5 volt. Also a valid choice, no obvious reason. Now the natural question is, okay, when we do that, okay, what is our output voltage then? And the operational amplifier really is a part that does that. It takes two input voltages and it generates an output voltage. And the question is, what is that? How big is that output voltage? And the answer here is minus 9 volt. Now, why is that so, minus 9 volt? The voltage at the negative input N minus is 1.5 volt. And that 1.5 volt, that is greater than the voltage at the positive input, because the voltage at N in plus is 0 volt. We can say that the negative input in minus, that this, so to say, the consequence down here, that in minus wins. And so the negative wins, the negative input wins. It has a higher voltage. And when the negative input wins, the output of the op amp, it falls down to minus 9 volt. It falls down to the negative supply border. I think that is really intuitive. You have the negative input wins, the output falls to the negative supply voltage. Okay, and then now you can think what we do next. We make another example. Now we leave the 0 volt at the in plus input, but for the in minus input we do a negative 1.5 volt. And what do you think happens now at the output? So now at the output we have plus 9 volts. So why is that? Because the voltage at the positive input, the 0 volt at in plus, that is greater than the voltage at the negative input and minus, where we have minus 1.5 volt. So that's a very natural thing. 0 is really greater than minus 1.5. That's pure numbers. 0 is greater than 1.5 minus 1.5. So the positive input wins. And when the positive input wins, what is the consequence? The output goes to the positive supply voltage. So it's always about, does the positive input win or does the negative input win? And winning means I have the higher voltage number. And yeah, with that, we can go to a little exercise together. Our choices for the negative input are minus 1.5. And our choice for the positive input is minus 3 volt. So you can stop the video for a second and ask yourself, what is the output? Most probably, after what you've heard. And the answer is that the output is negative 9 volt. And why is that? Because the negative input has minus 1.5 volt as input, and the positive input in plus has minus 3 volt at the input. So which one is numerically bigger? Yes, minus 1.5 volt is bigger than minus 3 volt. So you have the negative input winning because of this. Minus 1.5 being bigger than minus 3. Minus 3 is lower, obviously. So the negative input wins, so you have minus 9 volt at the output. So this result is shown here again. Next example. So now we put a plus 5 volt to the negative input and a plus 5 volt to the positive input. What do you think is the outcome? And the answer is 0 volt. So we have a case where the output stabilizes at 0 volt because we have no urgency to go towards plus 9 volt, and we have no urgency to go towards minus 9 volt because neither the negative input nor the positive input, neither two of them is the winner, and this then the output is then at 0 volt. In practice, this will be a little bit harder to get because we have things like input offset voltage, so-called, and this scenario won't be that easy. If it's not working, then please search about the input offset voltage. Then next example would be with positive voltages. We have plus 5 volt at the positive input and plus 3 volt at the negative input. And obviously 5 volt is bigger, so the positive input wins. Positive input wins. We go to the positive supply voltage, and the positive supply voltage happens to be plus 9 volts, so the output is again plus 9 volt here. So that's with the winner of the positive terminal and the negative terminal. The winner between positive input and negative input is just a thing to get you started with this. But there is an explanation, and you can use it, of course. And I often use it. But if you wanted to, would also be an equation to calculate what is the output. And the formula is the output you get when you take the positive input voltage number, you subtract the negative input voltage number, so this would be 6.5 minus 3, and you multiply that by 10,000 is written here. And that 10,000 is really a big number. If you do that for our example, we'll see that this causes problems, but for the moment, just take it. The problem is that we calculate like out is in plus, that's 5 volt, minus in minus, so the negative input, 5 minus 3 is 2. 2 times 10,000, those would be 20,000 at the output after this formula. And you ask, no, there's no 20,000 at the output. There is plus 9 volt because after our old rule of thumb, in plus is the winner. So we go to the positive supply voltage, plus 9 volt, and no, we don't have more. And you're right. So theoretically, we could go up as high as 20,000 volts, but only if we have 20,000 volts at the supply voltage. And naturally, when we hit the supply voltage, we have to stop at the output. We cannot output more than our supply voltage. If we had a supply voltage with 20,000 volts, we could go as high as that. And then, yeah, that would be it. But reality is we have to stop at 9 volt. And the next question will be, where do I get that random number 10,000 from? Why not a million or something? And so first, I want to tell you, because of this equation, out is in plus, minus in minus, times 10,000, you now get a sense of why it's called the operational amplifier. Here, really, what is amplified there is a voltage amplified, and it's amplified by the amplification means making something bigger or scaling something up, and then here really voltage is amplified, and it's amplified by a factor of 10,000, and that is really great. I don't know, perhaps you know about other forms of amplifiers, like with BJ3 transistors, and they have factors of a few hundreds. But this op-amp, it goes into the thousands, well into the thousands. And why do I pick the 10,000 from? Is this a realistic number? And the answer is yes, but let's see. And the let's see is in the direction of there are different op-amps. So you buy an op-amp from, for example, Texas Instruments, and you buy another one from another company, and they will probably have different values for what is 10,000 in my example. So that value of 10,000, that is called, in the formula, that is called the gain of the operational amplifier. And the symbol for the gain is the capital A. And we draw that formula again. And so we can write it as out is in plus, minus in minus, times A, or equally. Most of the time the A comes in front, but that's just something of a preference thing, how to put the letters. Often it is written as out equals A times in plus, minus in minus. And sometimes, often, the A is, there is a subscript after the A, and it's A, says AV, A voltage. There you know, AV is amplification of voltage, and that's where our 10,000 has been. So, and others say an operational amplifier that is very largely used and known in the industry is the LM358. You can remember that because that's, others call it a jelly bean component, and LM358 is very often used. And we'll look at what is what is the gain number in the LM358. And so LM358 is one of these components where many different vendors produce it. And I looked at the datasheet of Nonsemi for this LM358, and the circle column is the typical value. The circle column would be where the 100, the second middle column where the 100 is. It is open loop voltage gain, and it is 100 volts per millivolts if you read it. So the typical value here is 100 volts per millivolt, and if we mathematically calculate that, you can say it's 100 times the first 100 times, and volt per millivolt, it says, so we have 1 volt, the volt cancel out on the fraction, so 1 over, so no more volts, but just 1 over, and milli is a thousandths, 1 over thousands, and so we have 1 divided by 0, 0.001, and if you multiply that 100 with a fraction, you get 100,000. So I did not lie. 10,000 is real, and in reality the numbers are even bigger. In this example, we have 100,000 typical as a gain, as a voltage gain. So you can imagine again the difference being 2 volt. It's multiplied by the gain. We have then 20,000, and then going up to 20,000 is impossible. We stick to 9 volt. Some operational amplifiers can go up to plus 9 volt and minus 9 volt. Some operation, that would be what is called a rail-to-rail operational amplifier, being able to go to really precision plus 9 volt exact and minus 9 volt precision exact. That would be called rail-to-rail op amp, because you can go to the upper rail and to the lower rail with the output. But not a few of them, and in fact quite a few of them, cannot go to the rails. Some can go only as low as the lower rail, but cannot go up to the upper rail. So that's kind of an asymmetrical thing. And then perhaps you cannot go until 1.5 volt. You stop 1.5 volt before the upper rail, so this would be 7.5 volt. But there are others that can go rail to rail and that really go up to 9 volt, and we have chosen that our example would be a rail to rail operational amplifier, just for example. But the LM358, I think it is not a rail to rail operational amplifier, so don't pin me on that. And here is the thing, that if you put 0 volt at both inputs, oftentimes you don't get 0 volt at the output. That is the same example as with our plus 5 volt and plus 5 volt on both inputs, just because of the input offset voltage. And now we understand a little better. Here you see we have 2.0, and as the typical input offset voltage, so it can be anything from minus 2 until plus 2 millivolt, and this so let's say standard difference gets multiplied by the gain. So even if you put 0 volt on both inputs, if you have this 2 millivolt internal offset voltage of the op amp, you would have to multiply the 2 millivolt with a gain of 100,000, let's say, for the LM358, and then you would come out at 200 volts. And even if you have 0 and 0, well, the inputs, you then do not get 200. Of course, you are capped to the maximum, to the plus 9 volt here, and you would be quite disappointed why your setup isn't working. So just to hint you, keep in mind the input offset voltage. It won't make much of a difference in the following electronic schemas that we're looking at, because in some it matters, but I have to tell you, this open loop configuration here, where the output is such open to the right side, it's a rare usage of an op-amp. Most of the time you have some kind of so-called feedback. This means you connect the output line back to one of the input lines. That sounds weird, but you soon step into it, and it'll all make sense. And then if you do that, this input offset voltage, it won't be that big of a matter. So stay with me, we'll get into that. So this video is already 20 minutes long, and I decided to put the non-inverting amplifier into a separate video. You learned a lot, I think. We discussed a lot. And yeah, please watch the video about the non-inverting amplifier on my channel, or subscribe my channel. You get all the updates. Thank you.